Desley sir.
Hello, good afternoon.
Good afternoon, Dr. Nikhil Agrawal.
Yeah.
Welcome on this platform.
Hello, Dr. Arun sir. Yeah. Thank you for the nice welcoming. We are just waiting for the remaining participants to join, and then we'll start.
Yes, no problem, sir. No problem. No problem. I just want to check whether my staff is looking after that activities properly or not.
They are doing it pretty well, and from the last 3-4 days, I would rather say that the coordinators, they are continuously working day and night to increase the number of participants and have a huge participation.
Good.
I think they have crossed the number of participation by 300 and plus.
Yes, that is what we are expecting, because we have circulated this notification. Rahul?
Hello. Am I audible?
Yes, Rahul, you are audible, but your voice is very low.
80 participant झाले बाबा.
Rahul, can you put up a quick message on the WhatsApp group that the session is started? Rahul, if you can hear me, can you please just put up a message on the WhatsApp groups that we are starting with the session?
Yes, sir. I put
दिसले सर सुरू करायला हरकत नाही.
Yes, sir. Yes, sir.
हा करा ना सुरू. सर आलेत का? जगदाळे सर आलेत का?
सर जगदाळे सर थोड्या वेळाने जॉईन
झालेत
करणार.
का?
हा सर
करा सुरू करा.
Okay, sir. A very warm greeting to one and all present here. The standard of higher education is an important aspect of the nation's overall development. The goal and vision of higher education are to teach, train, conduct research, and provide community services. The research in higher education is regarded as one of the most important aspects of nation's development. It is an effective instrument for establishing a knowledge-based society. Without high-quality research, no educational institution can develop. In this modern era of research, computational chemistry and molecular docking are considered as an important tool to analyze the various properties of the molecule. Keeping all these things in mind, under the guidance of our respected principal, Dr. A.V. Patil sir, Department of Chemistry and IQAC of Mahatma Gandhi Vidya Mandir, Arts, Science and Commerce College, Manmar, in association with Board of Studies MGV, organized a national e-seminar on application of computational quantum chemistry and molecular docking. For this seminar, I heartily welcome guest of honor, Principal Dr. B.H. Jagdale sir, Trustee MGV Nashik, Chief Guest Professor Dr. K.H. Kapandi sir, Chairman BOS Chemistry Nashik, MGV Nashik, President of the program, our Principal Dr. A.V. Patil, then resource person for today's seminar, Dr. Nikhil Agrawal, Director, Center of Advanced Computational Chemistry Studies, New Delhi, Vice Principal and IQC Coordinator, Dr. P.J. Ambekar sir, Convener and Head of the Department, Dr. B.S. Desle sir, Academic Supervisor, Dr. S.S. Tambe sir, all HODs of various departments, Registrar Sri Samadhan Kedare sir, faculty members, and all dear participants who participate across the India. In preface, I would like to say that in present day, computer-assisted simulation, particularly those based on density functional theory, play a crucial role in exploration of various structural parameters of synthesized pharmacological compounds. Various softwares like games, Mopac, Gaussian, Spartan, etc. generally used for the computational study. I feel very proud to say that our ex-professor, Dr. A.B. Sawant sir, first time introduced DFT study in our institute, and under his guidance, our institute purchased Gaussian 30 program package, which is one of the milestone in the research journey for all of us. And presently, many researchers from our institute working with the DFT, and they publish many research papers in reputed international journals. Also, molecular docking remains an important tool for the structure-based screening to find new ligands and chemical probes. The scope of these hot topics is reflected in the seminar of this reflected in the registration of this seminar. I would like to tell our dignitaries that within 2 days we got 347 registration, and importantly, participants are from the various regions of India like Hyderabad, Chennai, Sikandarabad, Chandigarh, Valsad, Lucknow, Madurai, Jaipur, DNH, Guwahati, Tamil Nadu, Bhopal, Haridwar, Assam, Varanasi, Jhansi, Anandpur, Side Punjab, and also many other parts of the country. Few participants are also from the various universities of the world, like Islamia College University, Peshawar, Pakistan, Stony Brook University, US, University of Johannesburg, South Africa, Sinai University, Egypt, National Research and Innovation Agency, Indonesia, Tribhuvan University of Nepal. This huge response definitely inspired us to arrange this kind of seminar in future also. On the behalf of organizing college, I giving the best wishes to everyone for this seminar. Today, we are very fortunate to have with us the most valued speaker in this field of computational chemistry, Dr. Nikhil Agrawal. I would like to call Mr. Rohit Shinde for his introduction. Sir, it's over to you.
Thank you, Rahul sir. Thank you. Good afternoon, everyone. It's my privilege to introduce our research person, Dr. Nikhil Agrawal. Previously, he was working as a senior assistant professor in physical and analytical chemistry, Department of Chemistry, KIET Group of Institution, UP. Currently, he is a director of Center of Advanced Computational Chemistry Studies, New Delhi. Also, he is working as assistant professor at School of Basic Science and Research, Sharda University. He has a research expertise in the computational investigation of molecules via various density functional theory approaches. Dr. Nikhil Agrawal obtained his PhD in physical chemistry from the Department of Chemistry, IIT Madras in 2017, and his MSc and BSc from the University of Delhi. To his credit, there are more than 5 publications in the Journal of International Repute, including American Chemical Society and Wiley. He has also published a book in Lambert Publishing House, Germany. He participated in the International Conference on Modern Computational Methodologies and Challenges at the University of Washington, US in 2016. In 2021, the center's research activities gained huge momentum with the joining of 4 more dynamic researchers with expertise in various disciplines of computational chemistry who are actively working on industrial and academic scientific research projects. Over to Rahul sir. Thank you.
Thank you, sir. Now, I would request our respected principal, Dr. A.V. Patil sir, for the welcome address. Sir, it's over to you.
Am I audible?
Yes, sir.
For the today's one-day the today's resource person that he has accepted our invitation and is ready to deliver the lecture. On this occasion, the chief guest of this occasion is Dr. K.H. Kapadnis, the BOS chairman of chemistry, MGV.
I think there is problem. You're not audible.
Hello. Rahul sir, am I audible?
Right now, you are audible.
Hello.
Yes, sir.
Am I audible?
Yes, sir.
No one is giving me the response.
You are now audible.
Okay. So due to some internet problem is there today, internet is fluctuating. So because of that, some due to technical issues, I welcome all the
You are again not audible, Adil sir.
Actually, sir, internet issues there. So voice is not getting clear.
I am audible now.
Yes, sir.
Yes, you are.
There is a lot of problems with the internet connectivity. Dr. B.S. Jagdale sir, Honorable Principal Dr. B.S. Jagdale sir, the trustee of Mahatma Gandhi Vidya Mandir and the principal of LVH College, HOD Dr. B.S. Desley, all the department colleagues and all the dear participants, all the BOS members, I welcome on behalf of my college, Arts, Commerce, Science College, Myanmar. The very proper topic, the chemistry department has chosen the application of computational chemistry. I am also a researcher in electronics and physics. So I used to come across some chemistry part when I am working as on a pollutant gas sensors. There some chemistry part is required. And whenever I have gone through that, the computational chemistry approach is always helpful because it gives me the theoretical judgment that how the practically my sensor can work. So the DFT based computational chemistry approaches are working in our Malegaon center also. Dr. Sawant was looking after, now he is retired. So very important topic for the researchers, for the PG students. I'm thankful to the chemistry department that they have chosen the proper topic and the proper resource person. Once again, I welcome you all. Thank you.
Thank you,
Sir.
sir. Thank you, sir, for the motivation. Now, I would like to
sir.
Thank you, sir. Thank you, sir. Now, I would like to call upon our chief guest of this seminar, Professor Dr. K.H. Kapani, sir, to address the participants.
Am I audible?
Yes, sir.
Okay. Let me congratulate first to Myanmar College and Department of Chemistry for to have a webinar on such a wonderful topic, which is very important nowadays. The efforts taken by Chemist Department of Myanmar College as well as BOS members and convener and coordinator of the workshop are great, and they deserve the congratulations. As well, they have been chosen the topic, a very beautiful topic, which is applicable with a very knowledgeable person who has mastery in a computational chemistry. So the computational chemistry is a branch of chemistry that uses computer stimulation to assist in solving complex chemical problems. It exploits methods of theoretical chemistry incorporated into efficient computer program to calculate the structure, the interaction, and the properties of molecule. There are many softwares available for the same, like James, Orca, Columbus, Mopac, and Gaussian. Gaussian is one of the best computational chemistry software package launched in 1970 by John Popley and his research group at Carnegie Mellon University as Gaussian. It has been continuously updated since then. The name originates from Popley's use of Gaussian orbitals to speed up molecular electronic structures calculations as opposed to using slatted type orbitals. A choice made to improve performance on the limited computing capacities of then current computer hardware and Hartree for calculation. The current version of the program is Gaussian 16. More broadly speaking, we are in the process of purchasing the Gaussian 16 at LVH College. There are many methods available in Gaussian, but DFT is considered as one of the best methods for computing quantum calculations. Similarly, the DFT study can be performed by using appropriate functions and basic set by DFT computations. One can obtain lowest energy structure, that is HOMO-LUMO, NBO, NLO, NCI, UV visible spectra, FTIR spectra, NMR spectra, Raman spectra, etc. Likewise, one can study fluorescence and phosphorescence mechanisms. We can also study the reaction mechanism by DFT. Like this, there are many electronic and molecular properties one can study from DFT. And because of that only, I have been congratulated the Department of Chemistry, as well Board of Manmar College, and as well as the Board of Studies of Chemistry of MGVM, very knowledgeable person. You have been chosen as a research person. So without taking much more time in between the resource person and the audience, I'm again congratulate chemistry department and say the best of luck for the conduction of this particular webinar. Thank you very much.
Thank you, sir. Thank you once again. Now I would like to request our today's eminent speaker, Dr. Nikhil Agrawal, sir, to present his session. Dr. Nikhil Agrawal, sir, it's over to you.
Okay, dear. Yeah, I thanks to the organizing committee for arranging this seminar or the e-webinar, and within a short span, I would say that they are able to get a very good number of participants, maybe because the field is rather an emerging field with a lot of application in the both experimental front and as well as in the computational front. So without taking up much of our time, let me start with the session over here. So briefly, so we have divided the session into 3 parts. In the first part, we are going to deal with the theoretical aspect of the computational chemistry. And in the second part, we are going to have a brief of a practical demo, like what are the properties we can evaluate using the free software platform. And then in the third part, we will have a question and answer session. So briefly, let us go with the theoretical part. What is this computational chemistry and why it has gained a lot of momentum now? So computational chemistry, as like Professor K.H. Kapadnis has already explained a bit, that it is one of the branch of a chemistry in which we apply mathematical algorithms or function to evaluate the molecular level property, which are sometimes difficult to predict using experimental methods. So under the computational method, we have so many theories or so many models which can be implied that depends on the type of a molecular system which one generally adopts. Like as an example, generally we define the computational chemistry into 3 branches. The one which involves the quantum mechanical calculation, the second one which involves the molecular mechanical calculation, and the third one which employs the empirical or rather the statistical calculation. So let's have a brief discussion about what are these different methods. So quantum mechanical model, as the name says, it generally relies on the solution of Schrödinger equation. And Schrödinger equation, as we all know, that it is generally applicable for the microscopic system. So in principle, whenever we deal with the microscopic system, we try to perform the quantum mechanical calculation. But if let us say our molecular system is too big, in computation chemistry, we have a standard definition of what is a big system and a small system that we will in a minute. So if let us say we are working with a bigger system, the quantum mechanical equation, they will become very cumbersome, and even the software will then fail to converge the result. So in that case, we have to adopt a little bit approximated method, which is called as a molecular mechanical equation or molecular mechanical method. Under the molecular mechanical method, we generally apply the Newton-based mechanics. And as we all are aware of, the Newton mechanics is applicable for the macroscopic system. So first of all, we have to see, when we have to approach towards any computation chemistry-based project, we need to first see on what kind of a system we are working on. If our system is a microscopic in nature, definitely go for the quantum mechanical calculation. But if it's a too giant to be handled at a quantum mechanical level, then switches on to the molecular mechanical calculation. Now, what is the limit till when we can say that our molecule is microscopic or macroscopic? We'll see it in a minute. Now comes a question that why this particular field has gained a lot of momentum. See, as like the Professor K.H. Kapadis has already explained, that the Gaussian software, the most widely used software, it was developed long back, but that time the hardware was not much developed. But now you can say that the hardware which we basically use, they are very much developed. We have a huge RAM built computers with a lot of core processors and so on and so on. So therefore, the computers which we nowadays have, they are pretty capable of performing the majority of the quantum mechanical based calculation. And also, there are various theoretical researcher groups across the world who perform so many simulation, put up the approximation and simplify the various acceptable quantum mechanical model. Like the one method which is already studied is the density functional theory. So there are different theoretical researcher group which tries to simplify the equation even further so that the computation time will get reduced and the accuracy of our results will increase. So now comes a question that is there anything which cannot be computed, or is there anything which cannot be mimicked at an computational level? So starting from the atomistic level, moving on to the small molecule comprising of, let us say, some 5 to 10 atoms, then to the DNA, protein, three-dimensional crystals, surfaces, nanoparticle, protein, polymer. Nowadays, you can simulate each and everything. But yes, again, it depends on what system you take. You have to apply a suitable model. And which model has to be applied, we'll just briefly see it in a session. Now, I hope that few of you would be working in the solvent phase, liquid solvent phase based system. So the impact of the solvent and the solute, or I would say the interaction between the solute and the solvent, can be also very well defined using all this computational methodology. Again, when we experimentally work, we take up a high temperature, low pressure, high pressure, and so on condition that can also be mimicked using all this computational methodology. Starting from, as like the professor said, that we can evaluate the structure of the molecule, the most stabilized structure of the molecule, the transition state, the intermediate state, and so on and so on. We can also predict the various spectra, like starting from the IR spectra, reversible spectra, Raman spectra, circular dichorism spectra, NMR, and a lot of more. So in silico experiments can also be traced using the computational methodology. So in conclusion, we can say that the computational methodology which we have it with us right now nowadays, that can be applied starting from the small molecule to the bigger molecule, and majority of the property can be evaluated. And the accuracy nowadays it's pretty high as compared to the older days. Now, there comes a challenge like whenever we have to execute any quantum chemistry based project or any molecular mechanical based project, we have to ask very first question: what are like to compute? We have like an example. In our center, which is the Center for Advanced Computational Chemistry Studies, till now we have completed the training for almost like a 2005 candidates, but the majority of the candidates, they lack in the very first question. The question was, what exactly would you like to compute? So before you put up your hand on the computational chemistry as like your PhD student or maybe like a BSc or MSc student, you need to first know what exactly you would like to compute. Otherwise, the main software which we have it in a market, they are like a calculators and you can calculate anything on them. So first thing is, what do you want to calculate? Then after that, you have to decide which theory level and which model you will have to adopt. We will see what are the models which are available under the quantum mechanical model and in which case we have to apply which model. Then after that, we need to understand, okay, how these different models, they differ from each other. What are the approximations on which they are based, time which they take to provide as a solution, and the approximation, the accuracy which they provide. Because see, as a computational chemist, when we were learning this particular software platforms and computational chemistry, we faced a challenge in terms of the time and the accuracy. Our calculation used to take enormous amount of time. Sometimes it used to take even a month as well. And the level of an approximation and the accuracy, they were very bad. So therefore, we had to see like which model has to be adopted for which particular case. This has to be carefully picked up. We'll not go into the more into the theoretical part over here. So under the quantum mechanical calculation, there are various things which can be calculated. So we generally classify the properties into two types. The one which is the fundamental to every other researcher, like whether you are an organic chemist, inorganic chemist, or physical chemist, those fundamental calculation one needs to perform. But then depending on what is your specialization, maybe like you are working on metal complexes, maybe you are an organic chemist or inorganic chemist or whatsoever type, biological chemist, then the properties which are listed on the right hand side, you will have to adopt them. So what are the fundamental properties? The fundamental properties are the geometry optimization. What is a geometry optimization? It's simplistic meaning to evaluate the most stabilized structural form for your molecule. Now, as we all know that the majority of the properties of a molecule, they are structure dependent. As soon as the structure of the molecule changes, the properties of the molecule also changes. So therefore, the first calculation is always the geometry optimization. Whether you are taking a simple molecule or a giant molecule or crystal, unit cell, solid state, whatsoever. Then after that, sometimes it requires the frequency calculation. Now, what are the frequency calculation? We'll just have a practical demo over there for a while, and then single point energy calculation, then some spectra, transition state, and so on and so on. So these are rather the specialized properties which are the more specific to the individual research area. Moving ahead now, what is this molecular mechanics? So as like we have said, the molecular mechanical calculation, they rely on the Newton mechanical equation. So to make the session a little bit more interactive, otherwise it will become like a monotonous lecture. When we say that the molecular mechanical calculations, they are applicable for a macroscopic system and it relies on the Newton mechanical equation. So what do we think of that? The quantum mechanical calculations are going to yield us more accurate result, or is it the molecular mechanical calculation which are going to yield us the more accurate result? To the research scholar and the MSc student and the BSc student, this is the very first question of this session. Try to answer it. The quantum mechanical calculation or the molecular mechanical calculation, which will provide a better accurate result. The quantum mechanical equations, they rely on all sort of inter-electronic repulsion, nuclear repulsion, inter-electronic nuclear attraction, and so on and so on. Unlike in your Newton mechanics, it treats atoms just like the ball and the bonds just like the spring. So there is no concept of electron, proton, and so on and so on under the Newton mechanics. So what will you think of that? Which theory level will be more accurate in terms of result? Answer it very quickly. Excellent. So the answer is quantum mechanical calculation. So quantum mechanical calculation are nowadays a major thrust even for the macroscopic system. Like as an example, if in a principle we are working on the polymer, nanoparticle, or I would say solid state structure, two-dimensional surfaces. Now all these systems are macroscopic system. Sonia, your answer is incorrect. It is going to be quantum mechanical. So now what I said, the polymer, nanoparticles, two-dimensional crystals, three-dimensional surfaces, and so on and so on, all these things come under the macroscopic domain. So in principle, we are supposed to apply molecular mechanical calculation. But since we know that the quantum mechanical calculations are highly accurate, so therefore, generally nowadays people try to approach quantum mechanical calculation even for a macroscopic system. Now there it becomes a challenge. How to apply quantum mechanical calculation for a macroscopic system? Like as an example, if I take a case of a polymer comes under the macroscopic domain, but still we can apply quantum mechanical calculation by using the monomeric unit, because the majority properties of the polymer, they are going to be identical to the monomer. So therefore, if you replicate the monomeric properties, at least some properties of your polymer can be evaluated. Like the when you work on the nanoparticles, I don't know how many of you are working or planning to work on it. When you work on the nanoparticles, they are generally big and so many number of atoms would be present. So therein the cluster approach is there, which work at a quantum mechanical level and provide highly accurate results. Similarly, when you work on a solid state structure, therein you need to have the unit cell parameter. When you have the unit cell parameter, simply take up in a quantum mechanical calculation and get highly accurate results. So there are modern ways using which you can apply QM, quantum mechanical calculation, for even a bigger system. And that is what in majority of the research articles which are published nowadays, they demand. Now, so this molecular mechanical, we can leave it now. So these are few of the research articles from which generally we train our candidates. I'll not go into the much theory part of this quantum mechanical equation. So under quantum, as like I already said, the quantum mechanical calculation, it relies on to solve the Schrodinger equation for any big molecular system or small molecular system. It's a pretty complex equation, and to solve that pretty complex equation, it's very cumbersome task. So what happened? See, I'll have a time now. See what happened. There was a challenge in front of the scientific community. The challenge was to exactly solve the Schrodinger equation even for a macroscopic system, for a bigger system. I'll not call it as a macroscopic system. So what happened? Different theoretical research groups, they came up with the idea to put up the approximation to get this solution out of it. Let me simplify the thing. See, like if let us say I have to evaluate the value of a 1 by 100 in a very simple language, we can easily say that it will be equivalent to 0.01. But now when it comes to the evaluation for a value of 1 by 97, 1 by 98, that will take up a bit of our time to evaluate. But in a simplistic language, can we say that the value of a 1 by 98 will be equivalent to the 1 by 100? This is what is called as the approximation in the solution. By putting up these sort of approximation, what happened? Our calculation time decreases, but at the same time, what happened to the accuracy of our result? They also come down, because 1 by 98 can be equivalent to 0.01, but it will not be exactly equal to 0.01. So therefore, different theoretical research groups, starting from 1970s, I would rather say, they started to employ certain approximation in this mathematical model so that they can get the result at a faster speed. But again, we as all know, the moment we put up approximations in the calculation, our accuracy decreases. So let's come to the next slide over here very quickly. So in the literature, see, this is a published data in one of the very reputed journal of chemical theory and computation. Now this is published a long back. So over here, the density functional theory level is best. So generally the DFT comes in between the Hartree-Fock and the MP2. What are they? We'll spend some couple of minutes over here so that those who are new to this field, they will get a glimpse of it. So there are various methods under the quantum mechanical calculation. Now, why there are different models? Because they have all a common task. The task is to define the Schrödinger equation for a molecule and to solve it. But to exactly solve it without using any approximation, it's a big challenge. Or rather, it was a big challenge. So what happened? Different theoretical research group, they have employed various approximations to extract out the solution. The very first research group, I'll not call it as a very first research group, but one of the research group, Hartree and the Fock, they came up with a model, and within that model, they had certain approximation to solve Schrödinger equation. Then came density functional theory. Then after that, the Moeller-Closset calculation, which is known as MP2 calculation. Then we have couple cluster calculation. And now in a modern time, we have the couple cluster triple zeta potential calculations as well. Let me ask a few questions over here so that the session will become a little interactive. See, these theory levels are rather arranged in terms of their accuracy they provide. That means as you go down in the list, the level of accuracy for the result they provide, they are very high. Now, I have a very first question to all of you. If I proceed down in the list, the level of accuracy which the model gives me increases. That means what happened to the approximations which they uses? The approximations also increases or decreases as we go down in the list? Think of. Exactly. So this is the case. As you go down in the list, since the exactly everybody is correct over here, so that means the session is going pretty fine. So as we go down in the list, what happens? The accuracy of my result increases, and if the accuracy of my result increases, that means the approximations used in the calculation, it also decreases. But now my question is, what will happen to the time taken by the calculation? As we go down in the list, the time factor is supposed to increase or it is supposed to decrease? Exactly. So the time factor will increase. So therefore, we can always say that there is a trade-off between the time and the accuracy. The more the time you will devote for your calculation, the better accurate result you will get it. But it doesn't mean that we will have to spend our entire life to extract the 100% accurate result. Therefore, somewhere we have to balance. And how do we have to balance? Now in a literature, these methods and their applicability are more like calibrated. That means there are conventional rules, very informative and interesting. Thank you, dear. Please stay with us for the last because we have some practical session as well now. I'll just complete the theory part in a 5 to 10 minutes, and then we'll move over to the practical part. Yeah. So as like I said, that as we go down in the list, the accuracy increases. That means the approximation decreases, and as the approximation decreases, what happened? Tell me, guys. Now the question is, what will happen to the calculation time? It will increase. Now my question is, as I go down in the list, practically I need to apply couple cluster theory model for a bigger molecular system or smaller molecular system. What should be my choice? If as I go down the list, the calculation time increases. Think about it. As we go down in the list, what should be our choice for a molecular system? Shall we pick up a bigger molecular system or smaller molecular system for couple cluster calculation? Brilliant. Because the couple cluster calculation, now I'll conclude, because the couple cluster calculation, exactly, all of you are saying correct answer. So as like I said, as we go down in the list, what happened? The level of approximation decreases. And as the level of approximation decreases, Sonia, you are going incorrect. I'll answer it. So where I was, as the level of approximation decreases, then what happens? We need to put up a small molecule so that we get our calculation result. Otherwise, the calculation will take enormous amount of time, and majority of time it will fail. And that is the challenge which majority of the experimental researcher they face. They see somebody else's manuscript, they see like what model they would have adopted, and then they just blindly go with that model and apply that model on their calculation. A highly incorrect approach, because their molecular system will be different as compared to yours. And if that is the case, the theory level may be different. So be careful over here in terms of selection. Now, what are the selection rules? It's pretty simple. When your molecular system comprising of less than 8 or 10 number of atoms, and none of the atom possesses d orbital, it is always recommendable to apply CCSG calculation, because now my molecule is pretty small. But when the molecular size increases and goes up to 80 number of atoms, and none of the atom possesses d orbital, either vacant or filled, then you safely apply the MP2 molar closet calculation. And now the DFT, which is missing over here, the DFT model is generally applied when the molecule consists of less than 350 or 400 number of atoms, and the atoms have the liberty to have d orbitals as well. And the Hartree-Fock model, which we said it is highly approximated, so it is applicable for even bigger system, approximately 650 number of atoms. Now my question is, depending on your own research problem, all of you will be working on different research problem. Tell me which model will be more applicable for all of you. Is it going to be Hartree-Fock, DFT, MP2, or CCSG? Just now we explained the criteria depending on which you have to select the theory level. CCSG greater than less than 8 number of atoms. MP2 in between 8 to 80 number of atoms, but none of the atoms should have vacant or filled d orbital. DFT up to 350 number of atoms, an atom can have the d orbitals as well. Hartree-Fock even bigger than that. So now in the chat box, quickly reply which theory level will be most apt for your own molecule. Excellent. So as we can see, the majority of you reply with the DFT, and that is what is the reason. Like at the beginning of the session, Professor K.H. Kapadnis has explained that DFT has gained a lot of momentum because DFT has a huge applicability in terms of the molecular structure and the type of the atom which they can possess. So that is why in majority of the computational chemistry based article, you will find DFT being used extensively. Now, I'll not take the session more toward the theoretical part. This is one of the, again, research art, the data taken from the research article, and this particular graph, it defines, please carefully look over here. See, just now I explained the criteria depending on which you have to select the theory level. So this particular graph suggests the same thing. If the, see, this is the logarithmic scale. So if the number of atoms are less than 8, safely go with the couple cluster or multi-reference calculation. If the number of atom increases and goes up to 350 or so, apply the DFT. But as you can see that the accuracy will also come down. And then when the number of atoms goes even above than the 350, then go with the Hartree-Fock model. And by doing that, your accuracy will even further come down. So therefore, depending on what molecular system you have to pick up a suitable model. I'll see, this is one of the example which we generally go in the workshop. So this is familiar to all of you. It's an energy level diagram wherein we have the structure of the reactant, product, intermediate, and so on and so on. So these can be easily computable. We'll show it in a demo part now. Now, I want all of you to have a careful look over here. This is the data which is being published again by the Gaussian Research Group. Now, in this particular data, they have calculated the enthalpy change for a given reaction. The reactions are written over here. Please carefully look at each and every reactant and product and tell me, can I apply couple cluster model to all the molecules depending on the criteria which we have defined? See, just have a look on all the reactants and products which are written over here. Can we apply couple cluster model to all the reactants and products? Yes, because all the molecules comprises of less than 8 number of atoms, and none of the atom possesses d orbitals. So what happens? that research group had evaluated the enthalpy change for a given reaction at a couple cluster level, DFT level, and so many another level, and experimental values they had it with them. Now you guys have to quickly reply, otherwise we will miss the point. For the first reaction, which particular model is more closer to the experimental value? Is it the density functional model or couple cluster model? Tell me. This is the experimental value and these are the computed value. DFT, exactly. Now be very quick. For the reaction number 2, please have a look very carefully and quickly. For the reaction number 2, which model is more accurate to provide the enthalpy change of the reaction? Is it the CCSG or exactly? Go to the reaction number 3. Which model is more accurate? You have to be very fast, otherwise we will miss the point. Go to the reaction number 3. Which one is more accurate? Exactly. So we can see that CCSG is predicting a better accurate result. Now go to the reaction number 4. Be very quick. Reaction number 4. Incorrect. Exactly. So now there is a confusion which one is more accurate, because as you can see the experimental value is 164. Experimental value is 164. Computed value is 162 as per CCSG, which is less than 2 kilojoule per mole, and 166 as per DFT, which is 2 kilojoule mole as compared to the experimental. So both the models are accurate in terms of defining the enthalpy change for this reaction. And likewise over here we have CCSG, we have DFT. So now comes a question. Answer it very carefully. So being a practical researcher over here, what will be your ideal choice to select a theory level? Is it going to be CCSG or DFT as a researcher? Because see, majority of time it is, no dear, you will be in a trouble, because see, exactly, majority of you are replying with the CCSG because you are looking right now only at the accuracy of a result. But imagine CCSG model, it takes exponential time as compared to your DFT model. So therefore what will happen? If you will straight away go with the CCSG model, it will take enormous amount of time even as compared to your DFT. And let us say your accuracy improves by 1% or 0.1%, it is going to be meaningless over here. So therefore in under a practical situation, we start from the very small theory level, check the accuracy of our result, and if they are not accurate, then we switch on to the higher level of a model. So therefore our recommendation is first apply DFT calculation, check for the accuracy, because you have seen for few of the reaction, DFT also provided highly accurate result. So check the accuracy of your result. If they are not accurate, then switch on to the CCSG model if your molecular structure permits. Is this point clear to everybody or not? Is this point clear to everybody or not? Great. So with that, now let us move on to the next slide very quickly. So these are the energy level diagram which we generally compute in our workshop, which we take it in our sessions. So you can compute the ground state energy, the vibrational level, excited state energy, their vibrational level, the de-excitation pathway, the emission spectrum, fluorescence and phosphorescence. So these are the typical properties which we generally compute in our session. These are very easily computable at an equilibrium calculation level and non-equilibrium calculation level. Now I'll not take much of see, these are the orbital pictures. That means the some of you would have definitely heard about the highest occupied molecular orbital, lowest unoccupied molecular orbital. So these can be very easily calculated and can be picturized. Similarly, I hope some of you will be working in the field of metal complexes, and in metal complexes we have a metal to ligand charge transfer, ligand to metal charge transfer. So from where to where the charge transfer happens and what is the extent of it, that can also be computed pretty easily. So these mathematical equations, you don't have to go into the detail, because as a computational chemist, see, there is a difference between a computational chemist and a theoretical chemist. The solution part is basically for the theoretical chemist. They work on all these operators, mathematical equation to provide the solution. But as a computational chemist, we don't have to worry about the mathematical part. We need to know how to extract the properties from the software part, which is very easy as compared to the mathematical equation. Now, these mathematical things will not take it, otherwise it will become very boring. Now, coming to this particular slide. So as at the beginning of the session, Professor K.S. Kapadnis has already emphasized that in the market, there are various softwares which can evaluate the molecular level properties. So as it is correctly pointed out, the most widely used is the Gaussian. What is the reason behind that Gaussian is extensively used? Because it has a very brilliant graphical user interface. So therein you just have to go with a click, 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 and then your properties will be evaluated pretty easily. I'll not say easily, it will be like somewhat easily. Unlike your these free software platform like a Gammas, Oreca, MolePro, and so on, so on. And see, it's an old dated list. Otherwise, nowadays, even the Oreca and the Gammas, they support all the functionalities, major functionalities, which your Gaussian even has. So therefore, why Gaussian has gained a lot of momentum? Because of their very good graphical user interface. Otherwise, I'll take up a question in a minute here. So where I was, so otherwise, these software, Gammas, Oreca, they are gaining a lot of momentum because they are very quick to put up their update, and in their update they generally imply various theoretical model which Gaussian already has it. So therefore we have an advantage if we use the Oreca platform or the Gammas platform. They are free of cost. Anybody can use it for the academic purpose, and you can run the calculation using your own laptop. We'll just have a demo part of it right now. So with that, I'll see. This is the one of this is my research interest. So in my research group, we have close to 18 participants. I think some of you are already over here. So we have 18 candidates who are working on the research project, and our research project majorly lies to examine the molecular level properties towards their aggregation behavior, towards their solvation behavior, and so on and so on. The emission properties. So mark of a caution, or rather I would say conclusion over here. See, I am not going into the detail of what is the basis set and functional because that will take up an entire lecture. So under the computational chemistry, we have various theory level, and those theory level have their own approximation and they provide the accurate result accordingly. That depends from your system to system. But there is a one challenge which lies with every other computational chemistry software. What is that? Consider that these software are like the calculators and they will evaluate the property for you. But you have to justify whether the property which you have got is correct or not. Otherwise, see, sometimes what happens as a reviewer, we are facing a major challenge. Those people who learn the computational chemistry from some sources and don't go into the details of it, they just put up the calculation result in their manuscript and then submit it to the journals, and then it comes to us, and then it becomes a very challenging part for us to reject them. Why? Because they say that we have used highly sophisticated software, paid software, so our calculations are going to be correct. This is not a case. If you are not implying a correct theory level, basis set, functional, solvation model, and so on, your result, even though you are taking a free software or paid software, they can be meaningless. So be very careful over here. So I'll not take up much of a time over here in terms of the theory part. I'll rather go over the practical part now. So just like I have said that there are few properties which can be easily computed at the quantum mechanical level. So in our research group, we imply Gaussian software as well as the Oreca software. So these two software, they differ in terms of their applicability and also in terms of their cost. So Gaussian comes at a huge cost, and Oreca is one of the platform wherein we perform the quantum chemical based calculation, but at a free of cost. For the academic purpose, it's free. So let us first go to the first part of the session number 2, wherein we are going to see what exactly we can compute at the quantum mechanical level using free software platform. So the free software platform which generally people uses, they are Oreca along with the Avogadro. So we are already done with few of the calculation. So I'll just directly switch over to the result so that you can have a glimpse of what a computational chemistry can do for you. So we are already done with the optimization of one simple molecule like a methanol. Optimization means that we have already evaluated what will be its exact structure in its ground state. We have evaluated all the way its energy of the molecule, the bond distance parameter. Just see. So if you look at the value over here, it tells you what is the optimal distance between the carbon and the oxygen at a density functional theory level. You can also evaluate the bond angle between the 3 atoms of your choice. Like right now, we have evaluated the bond. Just a second. So if let us say we have to evaluate the bond angle between the 3 atoms, we can simply select and can read the value. And these are all according to the DFT model. So atomistic level parameter can be easily simulated. Their energy can be calculated. And if let us say you would like to see the dipole moment of the given molecule, so there is an option, select that. You will get to know what is the dipole moment of your molecule and what is its direction. various properties can be evaluated. And also you can see like if the optimization has occurred. See, I have one question for all of you. Try to answer it. I said the basic phenomena of the optimization is to decrease the energy of your molecule after each and every step. And how does it work? It works by decreasing the force acting on all the atoms. Let me show you something, otherwise it will become meaningless to say it over here. Let me click on the energy tab and click on the start option. Guys, observe it very carefully. Do you guys observe any changes in the structure parameter? Just a second, I'll revert back. Now see, do you guys see any structural changes and the energy changes when I clicked on the add option over here? Why? Because what software has tried to minimize the forces acting on all the atom and correspondingly try to decrease the energy as much as can be possible. So in a menu script, we have to provide the result in terms of their graph. Now in this graph, just a second. So like that, we do all the calculation and we get so many output and input files depending on the type of a calculation which we execute. Okay, let me stop this. Let me redrag and click on the extension tab. So I think the spectra window should open now. Yeah, it's over here. So in this window, we can see that when we have drawn the molecular structure, the software has tried to decrease the energy of your molecular system. And eventually, after the 6th or 4th number of a step, the energy of my system became constant. That time, the software said that, okay, we are done with the optimization. So that's how we are doing the optimization of the molecule. Afterward, as like professor says that we can compute the IR spectra. So to look at the IR spectra, we have already our result with us. I have one small question for all of you. Let us see how many of you will be able to answer it. We have computed the IR spectrum for the given molecule. Tell me how many total number of atoms we have in this molecule. If I'm not wrong, we have a 6th number of atoms. Am I correct? And for the 6th number of atoms, what will be the vibrational degree of a freedom? The vibrational degree of a freedom will be 12. It's a non-planar molecule. So accordingly, we are seeing 12 vibrational bands over here. You would like to, if let us say you would like to see the spectra part, you have the IR spectra in front of you. These you can match with your experimental part and can correlate with the properties. But see, these are the properties which as a computational chemist, we are not much interested of. We are rather interested to see the information at a molecular level. At a molecular level, we would like to see these vibration band corresponds to what? Like as an example, we classify the vibrational band in terms of their stretching and the bending. The stretching occur at a higher frequency, bending occur at a lower frequency. So I think of that being this 349 centimeter inverse. This vibrational band should be bending in nature. So if I click on the animation part, so you have the animation tab over here. If we click on the animation part, I hope majority of you would be able to visualize that there is no change in the bond length. Rather, there is a change in the bond angles only. So we can see that this particular vibrational band corresponds to the bending motion. Like that, you have so many vibrational bands, and each one of them can be very well explained in terms of their stretching motion and the bending motion. These are the hidden information we rather require it in a menu script. Similar to the IR spectra, we can evaluate the U visible spectrum of the molecule. How come? See, all these things we are done with the free software platform. Why we are emphasizing to use this free software platform? Because as a researcher, let us say you are working in a host institution wherein you have the paid software. But now if you will move on to some industry or an academia wherein you don't have the access of that software, then what will you do? In that case, you will have to rely on the free software. So I will rather recommend to start to use all these free platforms so that you don't have a dependency on the external fund. And one more question which was asked to few of the previous participants, that sir, is this free Oreca software acceptable in the literature? You can go to the Oreca, you can go to the Gaussian, to the Google, and on the Google just type Oreca. You will see that the Oreca software has crossed more than 3,000 citations within a span of, I guess it's 8 to 9 years. So that means already 3,000 plus manuscripts are published using this free platform. So it has no trouble in terms of accessibility in terms of the result. So we can have the computed U visible spectrum of the molecule as well. we can read their corresponding oscillator strength and the epsilon values, the lambda values. UV, we can leave it from here. And see, after that, as like the professor has already said, that we can evaluate the orbital pictures. So the orbital picture also we have already evaluated for a given methanol molecule. See, they are very simple to do it, and it's not much time consuming. We'll see to it in a minute. So if you would like to see how your different molecular orbital they look like, that can also be computed using the software platform. Now comes the question. No, there is a one more property which can be easily evaluated. I think we have already opened up the tab for it. Give me a second. Yeah, I think it's over here. No, this is not the case. Give me a minute. Yeah, it's over here. So as I don't know how many of you will be working in the field of thermodynamics or thermochemistry. In thermodynamics and thermochemistry, you will frequently see the internal energy of a system. So that can also be evaluated computationally. You can evaluate the enthalpy of your system at a given temperature, entropy of your system at a given temperature, internal energy, Gibbs free energy. These are the absolute energy which are very difficult to examine experimentally. So computationally, they can be easily mimicked off. So these are few of the properties which can be easily computed. Now, under the quantum mechanical calculation, there are so many other things which you can do it, starting from emission property calculation, charge transfer calculation, NMR spectrum calculation, Raman spectrum calculation. We have just shown the basic part of what you can do it using this free platform. Now, after this, now let's move on to the molecular docking. I think we have some 10 to 15 minutes with us. So see, what is a molecular docking? A molecular docking is a process which is the second part of this session. A molecular docking is a process which we basically use to evaluate how a microscopic molecule like a drug or a ligand interacts with a macroscopic molecule like a protein or the enzyme. So under this process, as we, okay, I'll ask a question over here. As I said, the molecular docking study we generally perform for a macroscopic molecule along with the microscopic molecule. So what will you answer that which theory we would be using or which model we would be using? Is it the quantum mechanical model or molecular mechanical model for the molecular docking? If I'll get a correct answer, that means the session is understandable to everybody. The question is molecular docking when we perform, which model we would be using over there? Is it the molecular mechanical or quantum mechanical? So majority of you are saying molecular mechanical. Now understand why is it so? Because see, when you take up a bigger molecule, for a bigger molecule, quantum mechanical calculation will never ever provide you the result. Forget about the accuracy, because bigger molecule will have huge, literally huge mathematical equation which software will not be able to evaluate. So therefore, in that particular case, you have to employ molecular mechanical calculation. So in conclusion, a molecular docking is a process in which we examine how a small molecule interacts with the macroscopic molecule, and to do that, we employ molecular mechanical calculation. Now, what are the software platforms which are available in the market, and what are the energy criteria depending on which we decide whether a given molecule can bind with the macroscopic molecule or not? So for that, we perform molecular docking using Autodock Vina and the PyMol. Both of them are comes at a free of cost. So that means anyone who is an academic person, they can use it for a free of cost. Now, let me just quickly show you, because we are having a very less time left with us. Under the molecular dynamic docking, let me put up as a Zoom call. So see, this is the last week result which we have it with us. I hope the screen would be visible to all of you. Now over here, we have a big giant protein structure. And in this big giant protein structure, we have a tiny ligand which is binded to some amino acids of this molecule. We have reached to this particular conformation after performing the molecular docking studies. How we did that, that is a little bit time consuming process. Otherwise, we would be able to explain it. But see, in terms of the result, what we can see, we have the microscopic molecule lying over here. It is not visible to me. So let me do one thing. Let me select this molecule and let me click on the zoom active selection so that it will be at least visible to all of us. So now see this tiny molecule, it is binding to the nearby amino acid. Maybe we can read the sequence of or the amino acid which are nearby to it. Let me change it to protein hide surface. So now see, this is the amino acid sequence or the polypeptide sequence which are rather bonded to the given drug. Now, if you click on the protein part, you will be able to see that these are the nearby amino acids which are rather interacting with my given ligand. And there is a one more thing which we can see in terms of molecular docking. What we generally get how many intermediate structures are there to evaluate this final conformation. So guys, I'm going to do one thing. I'm going to click on this arrow now, and you will have to see, do you people see any change in the position of a ligand or not? Do you people able to see the change in a position of a ligand or not? I hope everybody would be able to see it. So this is what is called as the molecular docking. Under the molecular docking, we give it a command to the software to change the position of the molecule under the protein cavity so that it will best bind. Now, how do we get to know which particular site is the most preferential site for the binding between the protein and the ligand? For that, we have the result in terms of their binding energy. And these binding energy values, you can read it out. So what does it say? That my very first structure, it has a very huge binding energy of minus 6.4 kilocalorie per mole, which overpasses the thermodynamical criteria or thermodynamical threshold of 4.8 kilocalorie per mole. So therefore, we can say that the given protein and the ligand, they biologically bind with each other. And similarly, you have so many intermediate structure, which although has a lesser binding affinity as compared to the most preferential site, but still all these intermediate conformation, they passes the thermodynamical criteria. There is a lot more we can see it over here, but due to the time constraint, I think we are already having a 133. These things we can show it over here. So in conclusion, what would we rather say? Under the computational chemistry, there are various branches. We have quantum mechanical calculation, molecular mechanical calculation. The quantum mechanical calculation are applicable for the microscopic system. Molecular mechanical calculation are applicable for the macroscopic system, like we are seeing on our desktop as a molecular docking. All these properties which we have seen under the table, they can be computed very easily using the free software platform. So our recommendation that if you are an experimental researcher, start to employ this computational chemistry and enrich your manuscript so that the probability or the exploration of the properties at a molecular level will be more enhanced. So with that, I thank all the organizing committee, the faculty members, the participants who have joined the session and remained till the end. Otherwise, usually in the webinars, people get bored, and towards the end, the number of participants reduces to the half. Noise. Yeah. Thank you, dear. So I thank.
Sir, your voice is not getting clear. Hello. 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 No, sir, your voice is not getting clear. Hello, sir. Hello, sir. Actually, your voice is not getting clearly, sir.
Yeah, I can hear the background also.
Sorry, sir.
Am I audible now?
Yes, sir. Yes.
So I hope the voice would have come out, but I hope I was able to. So with that, I thank all the participants for joining the session. I hope they would have found this section a little bit interesting. And then thanks to the organizing committee for arranging this session, all the coordinator, faculty members for joining the session. One small thing which I would like to share with all of you. We have seen a lot on the computation chemistry. If let us say somebody would like to explore it even more, we welcome you all to our website. On our website, we have all this workshop coming in the next week or next to next week. If you would like to register for them, please register. Maybe we can see you over there and have more exploration.
Sir, again your voice is. Sorry, sir. Again, your voice is not getting clear.
Because I can see that there is some noise from your side. Rahul, there is a background noise coming from your side. Can you mute yourself?
Okay.
Yeah, now it would be fine. Wait, just give me a second.
Yeah, I hope now I would be completely and clearly audible to all of you. So where I was in the session. Rahul, please keep yourself muted because there's a background noise coming from your side. So where I was over here that we have just seen a glimpse of what is a computational chemistry. If somebody would like to explore it in even a more, so you can come to our center. We provide online on different workshops. So we have the basic computational chemistry for all those who have the licensed version of the Gaussian. If somebody would like to learn the Oreca, they can register for this Oreca workshop. It's a 5-day workshop. We will be doing it in an online mode. And if somebody is interested to see the molecular dynamic studies, please register for this one. In case of any query, you can put me on my contact number, or maybe it will be better to put me on my email ID. So these numbers are mentioned over here. I'll put up what this web address to all of you, so that in case you have any question, you can text me over here. What about molecular docking? So for the molecular docking, we generally cover it in the MSG session, molecular simulation and the docking dynamic studies. Over here, we start from the software installation, then we go towards how to use the protein preparation, ligand preparation, docking analysis, and also we cover the molecular dynamics as well. The molecular dynamic studies we generally use to evaluate the time scale of any given chemical process. So therein we can cover it. Now, I would like to have the question from the audience side. Questions, please. Question from the participant side. Or otherwise, I'll hand over the session to the organizing committee. Rahul, now please you can take up the session.
Thank you, sir.
Again there's a background voice coming from the side.
Thank you, sir.
Most welcome. Most welcome, Rahul. Yeah.
Thank you for sharing your valuable knowledge with us. Definitely, it will be benefited for all of us. Now, I would like to request Mr. Abhijit Bukane to present the vote of thanks for this seminar.
Am I audible, sir?
Yeah, you are audible. There was an echo. There is a question by the Kuldeep that can we study the reaction mechanism by the DFT studies? Yes, you can do it. You can find out the intermediate structure, the transition energy, reaction state mechanism, and so on and so on. Somebody said that what is the best software to do the molecular docking using organometallic complexes? You can use Autodoc Vina, but that you will have to configure a little bit. How do we study temperature and pressure studies on a system theoretically? Perform the quasar study or quasar model. That can be ease of your task. NVT calculation can be done with the Gaussian, sir. It will be very difficult to do at the Gaussian end. So NVT calculation will be challenging for Gaussian. Yeah, the committee now.
Abhijit, sir.
Do we have class for the topic?
Shall I proceed, sir?
Just a second. Yeah. So if you guys have any more questions, please text us. That will be pretty easy for us to answer it. Okay. Now I'll hand over the session to the organizing committee.
Good afternoon to everyone, respected dignitaries, invitees, participants, and dear students. I am feeling honored to get opportunity to conclude today's e-conference on application of computational quantum chemistry and molecular docking, organized by PG Department of Chemistry in coordination with Internal Quality Assurance Cell of MGV's Arts, Science and Commerce College, Manmad. Organizing such a successful event cannot be possible without great preparation, wise working hands, support from every corner, and blessings. Now it is time to convey our gratitude to all who have extended their support to make this event successful. At the outset, on behalf of organizing committee, I would like to express my profound gratitude to our guest of honor, Principal Dr. B.S. Jagdale sir, Chief Guest, Professor Dr. K.H. Kapadni sir. Thank you, sir, for your motivational support and presence. I humbly thank Principal Professor Dr. Ravi Patil sir for his exceptional leadership. I also thank to Principal Dr. C.G.D. Gaukar sir on behalf of MGB's Arts, Science and Commerce College, Manmad. I also express my gratitude towards great speakers of today's e-conference who have enlightened us with his knowledge. Thank you, Dr. Nikhil Agrawal, sir. We are looking forward to see you again. I also thank to Dr. Vishnu Adore, sir, for all the support to make this event successful. I also thank coordinator of this e-conference, Mr. Rahul Shinde, sir. I also like to thank convener and HOD of Department of Chemistry, Dr. B.S. Desle, sir. I also like to thank Vice Principal of our college, Professor Dr. P.G. Ambekar, sir, Academic Supervisor Dr. S.S. Tambe, sir, Registrar Mr. Samadhan Kedare, sir, and all the organizing committee members, especially Mr. Rohit Shinde, sir, Mrs. C.K. Nerkar, madam, who have worked hard selflessly to make this event successful. Though in last but most important, our special thanks goes to all the participants who have attended this e-conference. Thank you all, and with the permission of all honorable guests and the principal of our college, I declare this e-conference is concluded. Thank you all.
Thank you, sir. Sir, one participant put their question in chat box. I think we will share the email ID of Dr. Nikhil Agrawal, sir. So you can communicate with him by the mail.
So our email ID is mentioned on our website. Yeah, correct. So our email ID is mentioned on our website. It's ADMIN. I'll write it over here. So you can forward your queries on our email ID. So there we can tackle it up.
Can we stop the meeting?
Rahul, Dr. Rahul, have you taken the attendance of the candidates? Because yes, that will be required.
In chat box, I put the link for feedback also. So all participants are requested. Please fill up that link for getting e-certificate of this webinar.
We have provided our email ID in the chat box. So if anyone has any question, please ask to us over the mail. Or I think majority of you would be having my WhatsApp number as well. So therein also you can ask us. Okay.
Can we end the meeting, sir?
Yeah, from my side, we are now on the committee.
Okay.
Dr. Nikhil.
Yes, please, sir.
Sir, you are a host for this meeting, so you should end from your side.
Okay, I need to end it up. Okay, I'll end it up.
Okay.
The recordings will be saved on my computer or will be on your computer. So who will be getting
in cloud? It will be in cloud,
sir. In our computer.
It will be in the cloud. Fine. So please make sure that we will be recording the attendance, not the attendance, rather the recordings as well for our record. So I request to Rahul or Rohit, Dr. Rahul and Rohit Shinde to provide us the recording as early as possible or share with us. Okay.
Yes, sir. Yes, sir. Sure.
Yeah. I hope every other participant would have enjoyed the session, if not much. Okay. We'll see in the future. Enjoy your day. Leave the webinar.